In this video, we're going to keep solving more trig equations, but once again, we're going to ramp up the level of difficulty a little bit, and these are going to require some factoring, which will eventually motivate us to develop and use Pythagorean identities. So the first set of problems we're going to do is not really materially any different from the ones we did last time. We're just going to have to, involve a little factoring. So we're going to look for values of x in the interval 0 to 2 pi that make these equations true. So the first one we've got is 2 sine squared x plus sine x equals 0. And I kind of like this one as a good one to start off with. But because we're not really used to factoring with a trig expression, what I would suggest is that maybe we consider this, instead of sine x, let's use a different letter. What if I had written this as 2t squared plus t equals 0? I think you would know how to solve this equation, right? You wouldn't try to directly solve at t or anything like that. It wouldn't get you very far. Okay, we're going to have to solve this one by factoring or by using the quadratic formula, but looking at this one and thinking about it critically, I would much rather use factoring. So I'm going to think, what's the greatest common factor between these two terms? That was a t, so I'll factor out a t and I'll be left with 2t plus 1, and that'll equal 0. And if two things are multiplied together to equal 0, we can use that zero product property. One of them has to be 0, so either that t is equal to 0, or maybe the 2t plus 1 was equal to 0. Now if 2t plus 1 equals 0, that could only happen when t is negative half. And so I could solve it out and say, all right, I get my values of t. I'll come back to that in a second. Okay, with 2 sine squared x plus sine x equals 0. Now, if you wanted to say let t equal sine x and proceed with what I did in green and just let that be your work, you can go ahead and do that. That's fine. I'm just probably not going to do that all the time. I'll probably just factor with sine because I think y'all can handle it. I'm going to factor out 1 power of sine x from that expression, right? And then I'd be left with 2 sine x, because I had 2 powers of sine originally. 2 times 1 power of sine plus 1, because I was to distribute that sine x back in. That would get me back to what I had originally. Okay, and that's still going to equal 0. And now I'm going to use the zero product property. And this should hopefully look familiar against what I've got in the green. Either sine x needs to equal 0, or 2 sine of x plus 1 needs to equal 0. And just like before, I could subtract 1, divide by 2, and say, all right, that gives me either sine x equals 0 or sine x equals negative 1/2, which is exactly what we saw in green. Okay, now that I've got it down to trig function equals number, I can go to this circle and think about, okay, where on the circle is, for instance, sine x equaling 0? Well, where is the vertical displacement from the x-axis? 0. Where is the y-coordinate on the circle? 0. Well, that would be, at the left and right extremes. Okay, and so I know what theta values those are. We're looking between 0 and 2 pi, including 0, not including 2 pi. And so that would be x equals 0 and x equals pi. Okay. Next, we want to think about, where does sine x equal negative half? And so I think about negative half, or half really, in the trig world. That's going to be part of a 30, 60, 90 triangle. So I'm going to go over here and say, all right, yeah, sine opposite over hypotenuse is going to be 1/2 over 1. And 1/2 is the short leg of a 30, 60, 90 triangle. So I've got to be having a 30-degree reference angle. And so those are like pi's over 6's. So, and if I'm thinking about where sine is negative, I need that 1/2, that vertical leg, to be going down, to be negative. So I'm looking in the third and fourth quadrants for 30-degree reference angle. Okay, I'm going down 1/2, and that's going to give me these 2 points there. And then I think about those between 0 and 2 pi. That's going to be pi plus pi over 6 is 7 pi over 6, and 2 pi minus pi over 6, that'll be 11 pi over 6. The next one I got for you is secant squared x minus secant x minus 2 equals 0. So again, I'm going to go off to the side and kind of factor this as if it wasn't trig. So I might say, all right, t squared minus t minus 2 equals 0. And this is the type of thing I'm definitely good at factoring. This is going to be t minus 2 times t plus 1. And if I wanted to know where these things multiply together to equal 0, that would either be t equaling 2 or t equaling negative 1. Okay. So if I want to factor the expression that's written in black, like the trigonometric expression, I'm going to kind of use the green as my guide. Okay, t minus 2, t plus 1. I should have secant x minus 2 times secant x plus 1. And then, well, now I've got it factored, and I can set the things equal to 0, right? I can say secant x minus 2 equals 0, or maybe secant x plus 1 equals 0. I can solve these for secant x, but that doesn't do me all that much good. I'd rather have it in terms of sine or cosine, or maybe tangent if I had to. And so I know that secant of theta is 1 over cosine theta. So if I want to get cosine theta, I can take 1 over secant theta. And so if secant x equals 2, that means cosine x will be a half. And if secant x is negative 1, that means cosine x will be 1 over negative 1, which is going to be negative 1. Okay, so I've got all these things. I've got it down to trig function equals number. That means I can go to the circle. And I'm going to start just by thinking about where cosine x equals a half. Okay, and so you think about a half, and that's the short leg of a 30, 60, 90 triangle. I didn't draw the triangle this time, but, I'm thinking, if it's the short leg, that means and that's the horizontal leg, that means the vertical leg is going to be the tall one. I'm looking at a 60-degree reference angle. And so I'm going to go right of the y-axis by a half, which is really not very far. And then I'm going to mark off those spots on the unit circle, and I'm going to say, all right, that looks like pi over 3 and 5 pi over 3. And then I'll think about the other equation that could possibly give me solutions. Cosine x equals negative 1. Well, that's when the horizontal displacement from the y-axis is negative 1. I'm all the way to the far left edge of the unit circle. That's going to be right there. And that's an angle of pi, so I've got x equals pi as one of my solutions there. Now this third one's a little different. This has got sine and cosine in it. And so this is kind of getting us towards what we're going to have to do here in a couple of minutes, which is, maybe make some substitutions to write an equation in a more convenient form. But for now, I am going to be able to factor this. We need to start by setting the expression to 0. So I'm going to subtract that square root of 3 sine x from both sides of the equation. Okay, and then I'm going to think about factoring. I'm going to think, first of all, it doesn't really look like a quadratic to me. I don't see anything to the second power. So is there anything I can, like a greatest common factor, I could factor out? And yes, there's a sine of x in both terms of this expression. So I can factor out that sine x, and I'll be left with that sine x multiplied by 2 cosine of x minus the square root of 3. And now that I've got it factored, two things multiplied together, I can say, okay, one of these things has to equal 0. So either sine of x is equal to 0, or maybe 2 cosine of x minus the square root of 3 is equal to 0. Okay, and 2 cosine of x minus square root of 3 equals 0. That would happen when cosine x was add root 3 divided by 2 root 3 over 2. Okay, now that I've got it down to trig function equals number, I can, pull in a unit circle and start thinking about where that happens and what kind of angles give me solutions to these equations. Well, the first one, sine x equals 0. Okay, I'm thinking of where the distance from the x-axis vertically is 0. Okay, that'll be on the x-axis. That's x equals 0, x equals pi. Okay. Then I'll think about where is cosine x equal to root 3 over 2. Root 3, I'm thinking 30, 60, 90 triangle. Root 3 over 2, that's the long leg. Okay, cosine's the horizontal leg, so the longer leg is the horizontal leg. That's going to correspond to a 30-degree reference angle. And then we think about where is cosine positive. Where is that horizontal displacement from the y-axis positive? Okay, over to the right of the y-axis in the first and fourth quadrants. I'm going to go that far over and go to my 30-degree reference angle spots, which will be, just right there. And I'll see that, okay, that's going to be pi over 6 and negative pi over 6, but it asks for solutions between 0 and 2 pi, so negative pi over 6, that's like 11 pi over 6. And so I'll just report my answers there, and I think that's a good collection of factoring problems. And if we tried to extend these techniques to an equation like this one, we would not be able to go any farther, right? It's like we're not going to be able to solve this because I can't factor anything out of this equation. I need to rewrite it in a more convenient form. So this is why, these are the types of equations we're going to be able to solve. I think you can see that when t equals 0, I've got a solution, right? Sine of 0 is 0. By square of 0, it's still going to be 0. 0 plus the cosine of 0 is 0 plus 1, and that's going to equal 1. So there's solutions out there that weren't that hard to find. It's the first thing I thought of. And so we should be able to solve this one. I think that's kind of the idea here. And so we're going to develop a formula that we could use to help us solve this. All right, so we're going to develop Pythagorean identities here so that we can solve that equation up above. That's our primary motivation right now, and that will be good enough. And aside from the fact that this is something we have to know for AP Pre-Cal. So I'm going to just kind of take us back to the unit circle and ask you to think about an angle in standard position, right? Something about like that, theta radians. And then I'm going to do what I did pretty much every time is draw a reference triangle. Okay, I had a side length there, and then I went up to the point of intersection, and that created a right triangle. Okay, on that right triangle, the hypotenuse was always 1 because it was a unit circle. And then, a couple units ago, we put in a lot of work to discover that the horizontal leg of that triangle was represented by cosine of theta, and the vertical leg was represented by sine of theta. Okay? And so that's just a general diagram of what we got going on here. And it's probably good to be reminded of that on a daily basis, but what we need to do with this is we need to apply the Pythagorean theorem. Okay, we know the Pythagorean theorem. We've worked with it for a very long time. We know that a squared plus b squared equals c squared. What I want to remind you about that is that c needs to be the hypotenuse, right? So if I was going to apply the Pythagorean theorem to this right triangle that I've drawn in on the circle, I'd need to start with the fact that, okay, well, c is 1, because c is the hypotenuse of the right triangle. And then, that'd be like a squared, maybe cosine of theta squared, plus b squared would be sine of theta squared. And then if I look down at what I'm trying to show, sine squared theta plus cosine squared theta equals, well, that's pretty much what I've got here. I've got sine squared theta and cosine squared theta. They're just written a little bit differently. And that's equal to 1 squared, and 1 squared, well, that's just 1. And so that's the identity. Sine squared theta plus cosine squared theta equals 1 for every value of theta. Okay, so now using that, we're going to go back up above and solve that equation. All right, so the thing that was causing us to not be able to factor was the kind of the mix of sine and cosine. So I want to get this to like one type of trig function so I can hopefully factor it. That's the goal here. And so really, it's like I could probably go to the yellow equation and solve for cosine if I really had to, but that's not going to be the way to go. We really don't want to do that. We're going to want to get rid of the sine squared t. All right, so I'm looking at this one here, and it's like, okay, we can work with that. And we're just going to solve for sine squared t right here. Sine squared t is going to equal, I'll subtract a cosine squared from t from both sides, and I'll have 1 minus cosine squared t. So I'll make that substitution. I'll say, all right, that's now 1 minus cosine squared t. And then I'll kind of just like, maybe get rid of those parentheses and say, all right, well, parentheses didn't really do anything. The color, I was just illustrating you where it came from. But when I write like this, I think it's more obvious that I'm going to need to start by subtracting 1 from both sides of this equation. And now that it's set to 0, I might like to factor it. But I really don't like the fact that the leading coefficient's negative 1. So I'm going to factor out the cosine and the negative 1. So I'm factoring out negative cosine of t. And I'll be left with 1 power of cosine t and then a negative 1. And if I think about distributing it back in, that would give me what I had originally. And now it's factored, so I'm going to set each of the factors equal to 0. So either negative cosine of t is equal to 0, or cosine of t minus 1 is equal to 0. And that'll give me either cosine equaling 0 or possibly 1. Okay? And now that I've got it down like that, I can bring in a unit circle and think about, all right, well, where is cosine of t equal to 0? Well, where the horizontal displacement from the y-axis is 0. So that's going to give me t equals pi over 2, also 3 pi over 2. And I think about where's cosine t equal to 1. That would be right over here. That's 0 and 2 pi. But I think we're still, kind of operating under the directions just 0 to 2 pi, including 0, not including 2 pi. So that'll be our solution for that one. And so here we see, like, if we just make a little substitution using the Pythagorean identities, then we're able to solve an equation like this. All right, now there's also 2 other equivalent forms of this identity, and I'll be honest, when I was in pre-cal, I just memorized them, and I then forgot them pretty soon after. But the first time I taught pre-cal, the guy that I was teaching it with showed me that, like, all you really need to remember is sine squared theta plus cosine squared theta equals 1, and then we can develop the other ones from that. That was really helpful for me, so I'm going to show you the same process. So we're going to develop 2 new identities, so I'm going to copy down the identity we know twice. And I didn't write it down for you to start with because if you're trying to memorize something, which you need to know this, like just at a moment's notice, moving forward, you need to know that sine squared theta plus cosine squared theta equals 1 for every theta. It really helps to write it down in your own handwriting or say it out loud with your own voice. And I know you're a little embarrassed to be saying out loud sine squared theta plus cosine squared theta equals 1 a whole bunch of times, but it would help. Okay, so we're over here, we've copied it down, and what I'm going to do is I'm just going to divide everything through by the same thing. Okay, that'll be fair to both sides of the equation, that'll preserve the equality. So on the left, I'm going to divide everything by cosine squared theta. Okay, so just all of these things, turn them into a fraction. Okay, and then I'm going to think about, like sine over cosine. We know that's equal to tangent, so sine squared theta over cosine squared theta, that should give me tangent squared theta. And then I'm going to add cosine squared theta over cosine squared theta. That should be 1. And then that's going to equal 1 over cosine squared theta. 1 over cosine theta is secant theta, so this should be secant squared theta. And that's our second Pythagorean identity. And then on the right, what I'm going to do is the exact same thing. I'm just going to divide everything by sine squared theta. And so I'm going to start off with sine squared theta divided by sine squared theta. That's going to be a 1 plus cosine over sine. That's going to be cotangent. So 1 plus cotangent squared theta equals 1 over sine squared theta. That'll be cosecant squared theta. And that's the other Pythagorean identity. And I don't recommend that you go and memorize these because I think that you can reproduce these formulas when you need them rather than just having to know them. Because there's so many things that we have to remember. I think this is just one too many. Especially when we go forward next time when we do the sum and difference identities, that's a lot to remember. Okay, so let's just only remember that sine squared theta plus cosine squared theta equals 1, and then because I think a lot of y'all are going to just be able to write that down and then visualize yourselves dividing through by cosine squared theta or sine squared theta, and I'll show you a couple of examples of what that looks like when we need to use those. Alright, so in this course we do need to be able to find equivalent representations of trigonometric functions, which is pretty much going to be like, in multiple choice, f of x equals this. Which of these could also represent f of x? But in a free response scenario, I've seen a couple where they're going to give you these extremely specific instructions, like simplify this expression to be a single trigonometric function raised to a power. Okay, we can do that. Alright, well, first thing I see is this 1 plus tangent squared theta. And maybe you just see the tangent squared theta, and you're like, I probably am going to need to substitute on that with the Pythagorean identity. Okay, and if you don't see that yet, well, that would not surprise me because you're brand new to it, but you will with time. Okay, so I'm going to say, all right, I don't remember what the formula is. It might be 1 plus tangent squared theta. Let's just go ahead and figure it out for ourselves so we can be certain. What we know for certain is that sine squared theta plus cosine squared theta equals 1 for every theta. And then I'm going to go and I'm going to divide everything through by cosine squared theta. And it needs to be cosine squared theta because I need the tangent squared theta. And the only way I can get tangent is with sine divided by cosine. So I see that sine squared theta, and I want to divide that by cosine squared theta so I can make sure to get a tangent squared theta. All right, you can't see everything. My face is partially blocking it, but I think it's going to be all right. Okay, from there, I've got sine squared theta over cosine squared theta. That's my tangent squared theta. Plus 1 equals secant squared theta. All right, so I'm noticing I'm trying to substitute on this 1 plus tangent squared theta. I've got a formula for it right there in green. That's secant squared theta. So I'm going to make that substitution. I'm going to say that this equals secant squared theta divided by cosecant theta times secant theta. And then I'm going to just I kind of want to cancel off, but it's been a while since we've done that type of thing, so I'm just going to rewrite it. 2 powers of secant theta times secant theta. Right? And then I've got these secant thetas that are ready to cancel off, right? I wrote them right above each other. And we can do that, and so we'll cancel those terms off and say, all right, well, this is equal to secant theta over cosecant theta. And then, okay, well, I'll think about secant, that's 1 over cosine. And cosecant is 1 over sine. So if I was to just send them to the opposite sides of the fraction and write them as the normal functions, we'd have sine theta over cosine theta. And that's tangent theta. So that's what we're saying, a single trigonometric function raised to a power. And, I'm sorry that it wasn't raised to the second power, but that would have required us to do all sorts of stuff to the original expression, and we're not trying to do that to you. And the last time I taught Precalculus, we did a lot of trig identities, and a lot of them were pretty tough. And it doesn't seem like that's a big focus in AP Precal. We need to know our identities. We need to know Pythagorean identities. We need to know double angle, which we'll find out about next time. All the reciprocal identities, which we already know about. And also, what was the last one? The sum and difference identities, which we'll also learn about next time. But as far as doing the complicated proofs, that doesn't seem to be part of this course. Okay, with one like this, we run into a 1 plus cotangent squared theta, and that's the type of thing, okay, that cotangent squared, that's probably going to need a Pythagorean identity. So we, once again, start off with sine squared theta plus cosine squared theta equals 1 for every theta. And if I need cotangent, I need cosine over sine. Okay, so that's going to be dividing everything through by sine squared theta. And then I'll have 1 plus cotangent squared, which is exactly what I'm looking for. This is fortunate, equaling cosecant squared theta. Okay, so I'm going to substitute that for 1 plus cotangent squared theta. And so I'll have cosecant squared theta divided by sine cubed theta. And maybe if you didn't see what I was talking about the last time when I just kind of switched stuff around, I'll be a little more explicit here. Sine in the denominator, that's cosecant. Okay, you know that. You know your reciprocal identities. So what I'm going to do is rewrite this as cosecant squared theta multiplied by 1 over sine theta taken to the third power. It would be the same thing. And 1 over sine theta, that's cosecant theta. And so that's where I'm going to get 3 powers of cosecant over there from the sine cubed in the denominator. And I already had 2 powers of cosecant from the numerator, so I would add those together and get 5 total powers of cosecant theta. Now, the last example I've got for you, it doesn't look like one that's going to use Pythagorean identities because it doesn't have any squares in it, but it will. And so it's going to say write the expression as the product of 2 trigonometric functions. And so what we're going to do is we're going to start off by rewriting these in terms of sine and cosine. Okay, we know that tangent is sine over cosine, and cotangent is cosine over sine. Okay, and if I want to combine these into a single expression, which is my best chance of getting a product, I'm going to need a common denominator. And so I'm going to say, all right, well, the common denominator, if I have a cosine theta and a sine theta, it's just going to have to be the product of the two things, cosine theta times sine theta. So I think that first fraction, what do I need to multiply it by on top and bottom to get a denominator of cosine theta sine theta? Well, I need to multiply by 1 power of sine. And if I multiply by 1, sine theta over sine theta, I'm not changing the value of the fraction, so I can get it ready to combine with a common denominator. I can do the same thing with the second fraction and think about it. Well, I'm going to need to add a cosine theta over cosine theta, multiply that in, so I can get that good denominator. I can combine those with the common denominator, and I have negative sine squared minus cosine squared. It's like, ooh, that looks kind of familiar. I'm going to factor out the negative, see what happens. Okay, I factor out the negative, and I'm left with the negative of sine squared theta plus cosine squared theta. And hopefully at this point, you've written it down enough times, you know what that equals. I'm not going to really belabor the point, but sine squared theta plus cosine squared theta does equal 1 for every theta. I'm going to substitute 1 in there for that highlighted expression. And I'm going to say, all right, negative 1 over cosine theta sine theta. And said product of 2 trig functions. Well, okay, 1 over cosine is secant. 1 over sine is cosecant. So I'll call this negative cosecant theta secant theta, or the opposite. All right, yeah, 2 times 3 is the same as 3 times 2. It's going to be all right. All right, so I think that's going to be all for the examples in this one. I think there were some examples up earlier that had to do with factoring. I'll save those for when we review for the test. That's going to be all for this video. Thanks for watching.